thinking a little more about energy. Just remember where we are. The fundamental idea is that work, at least when it's work done by the net external force, changes the energy. That's how energy is given to or taken from a system. And energy change could come about by changes in one or more of the four different types of energy that we're thinking about: kinetic or gravitational potential or elastic potential or thermal. And then remember, of course, our rule for calculating work. The numerical value of work tells how much energy is given to or taken from. And here's our rule for calculating the work done by the net external force. Force, displacement, and cosine of the angle between the force direction and the displacement direction. So let's consider this situation here. It's a daredevil jumping off a cliff, and the leg is connected to a very, very flexible, long flexible rope, bungee cord or something like that. So when this guy has fallen 40 meters, now the rope is completely unwrapped, completely unfurled. The rope itself is 40 meters long, and now as this guy continues to fall beyond this point, the rope begins to stretch, and so the rope is now going to act like a spring, act like a stretched spring, which will try to snap back to its original shorter length. And as it tries to snap back, it's going to pull up on the diver, and an upward force will eventually slow the diver down to a stop. So the diver's final location, when the diver stops here, is a total of 60 meters below the place from which the diver jumped. Right, 40 meters to just unwrap the rope, and then the rope stretched 20 meters before it was able to bring the diver to a stop. So the final velocity, of course, is 0. And this rope is acting like a spring, so the force that it applies to the diver is a spring force. And just a reminder of how those spring forces work. Right, the spring force is just proportional to the displacement that the end of the spring feels when it's being stretched away from its normal undisturbed location, or compressed away from its normal undisturbed location. And put a minus sign here to indicate that the spring force always points opposite to that displacement, because the spring force is always trying to undo that displacement and make the spring snap back to its original undistorted shape. If you stretch a spring this way, you've displaced the end of the spring that you're holding onto this way. So there's a displacement this way, and the spring force tries to undo that displacement by pulling the opposite way. So this rope is being stretched this way, so the springiness in the rope is trying to undo that stretching and pull the bottom of the rope back to its normal unstretched length. This K constant basically measures how strong the spring is, how much spring force you get, because obviously if you have a bigger value of K, for any amount of stretching, that would give you a stronger spring force. So in this question, we're asking basically how strong is the spring force in this spring-like rope. In other words, we're asking what's the value of K for this particular case. that's the question, and we're going to answer it by thinking about energy. So, of course, the first thing we have to do when thinking about energy is decide what's in our system, because energy is a property of a system, and we want to have a system that will lead us to think about things in as simple a way as possible. So we want a system that is so-called an isolated system, that is a system that doesn't have any work done on it by outside forces. No work done on it by outside forces means no change in the system's energy. The system's energy stays constant, stays conserved. And we have those 4 rules that tell us what should go into a system if we want it to be an isolated system, if we want it to be a system with no outside forces, if we want it to be a system that keeps its total energy constant. First rule, anything moving should be included in the system. It's got kinetic energy, so that energy is going to be part of the system's energy. So in this case, the moving thing is the person doing the diving. Rule number 2 tells us that if the movement involves a change in elevation, you have to include the Earth in the system. You include the Earth because a change in elevation means a change in gravitational potential energy. And gravitational potential energy, like most kinds of potential energy, is something that is shared between 2 things that are interacting by a gravitational force. In this case, the 2 things that are interacting are the diver and the Earth. So both of them share that potential energy, so both of them have to be in the system if we're going to say that that energy is part of the system. It doesn't make any sense to say that gravitational potential energy is in the system when only one of the 2 objects that share the energy is in the system and the other one is outside. It doesn't make sense to talk about the gravitational potential energy of a system unless both of the things that share that energy actually are in the system. So we include the Earth. And then the third rule, if there's any elastic object that's being stretched or compressed or bent or anything like that, it's gaining some elastic potential energy, so we'll have to include that elastic object, and that's exactly what's happening here. The elastic rope, acting kind of like a spring, is being stretched. So it's gaining elastic potential energy. And if there were any friction, we would have to include all objects that are involved in those friction forces, but there isn't anything like that in this case. There is a drag force, of course, on the diver as the diver moves down through the air, and drag forces actually do act just like friction forces in many ways, but to keep things simple, we'll say that the drag force is really small compared to other forces, so that it doesn't really play a significant role. So no friction, not even any friction-like forces such as a drag force. So we don't have to include any of those kinds of things. That's what's in the system. And the important part about deciding what's in the system is that it tells you a little bit how to think about the forces. And what are the forces in this case? Well, the diver is falling. There is, of course, gravitational force, the weight pulling down, and then the spring force from the springy rope pulling up. And since there's very, very little drag force, those are the only 2 forces. Now, we need to ask, are those internal forces or external forces? And looking at what's in the system tells us this force comes from the Earth, which is part of the system. And then, of course, that gravitational force acts on the diver, who's also part of the system, so that force is entirely within the system. being entirely within the system, remember what that means. When that internal force does work, it gives energy to or takes energy from some part of the system and just gives it to another part of the system. So that energy stays in the system. It just might take on a different form and might be associated with a different part of the system. But work done by internal forces doesn't change the total energy of the system, moves it around from one part of the system to another, but stays inside. So it does not change the total energy of the system. And likewise, this force, the spring force, comes from the rope, which is part of the system, and acts on the person who is part of the system. So that's an internal force also. And the important part there is that now all the forces are simply internal forces. There are no external forces. So then clearly there is no work done by external forces because there aren't any external forces. The work done by external force is zero. So you have zero energy change in the system. The system's total energy stays constant. Different types of energy will change. Individual different types of energy will change, but the overall total energy will stay the same. Okay, now let's think about each of these terms here. We need to see whether each of those terms is zero or not zero, and it's also helpful if they're not zero to see which ones are positive and which ones are negative. Well, there is no work done by external forces, so there is no change in the total energy. That is zero. And likewise, when you compare the start, when the person is standing here getting ready to jump, compare it to the end when the person has been falling but now is brought to a stop, final velocity of zero, we see there, comparing beginning to end, there is no change in the kinetic energy. There was kinetic energy in between, but the initial velocity was zero before the jumper started the jump, and the final velocity is zero, so the initial kinetic energy is zero. And the final kinetic energy is exactly the same, zero. Comparing beginning to end, there's no difference in the kinetic energy. And that's what change in kinetic energy means, just the difference between the beginning and the end. The gravitational potential energy decreases. Gravitational potential energy is directly proportional to elevation, and as the jumper went through the dive, the jumper's elevation decreased. So gravitational potential energy must decrease. So that's a negative change. There is a change in the elastic potential energy. Initially, the rope is not stretched. In the final state, the rope is stretched by 20 meters. So when the rope gets stretched, it gains. When the elastic object is stretched, it gains elastic potential energy because work is done on it by the force that is pulling and doing the stretching. So initially, no stretching, so no elastic potential energy, but in the final state there is stretching, so there is elastic potential energy. Elastic potential energy increased from zero to something other than zero, so something greater than zero, so it's a positive change, an increase. And since there was no friction, there's no change in the thermal energy. Change in thermal energy happens when there is friction. So when there's no friction, there's no change. And that's what we have. And then the next step is just to write out that basic energy change equation in detail. Use our defining equations for kinetic energy and potential energy to write out this equation in terms of masses and distances and values of the spring constant and displacements and so forth. So let's see how that looks. One thing to do that, we want to define our coordinate system for purposes of giving different numbers to the elevations. Here's the final location, or the final elevation. We'll say that's the bottom of the jumper's motion, so we'll call that the 0 level of elevation. And then the initial level of elevation is 60 meters above that. $20 from the stretching and 40 meters from just unwinding the rope. Now, let's write that out. Left-hand side, change in total energy is just plain 0. And then, of course, we only need to write out the non-zero terms. So that term is 0, don't need to deal with it. This term is not 0, so we need to write it out. And change in gravitational potential energy is just the final minus the initial change in potential energy. So final is mg, final elevation, minus initial, which is mg initial elevation. And then the change in elastic potential energy is not 0, so we need to write that out in detail. That's just final elastic potential energy minus initial elastic potential energy. And to write that out, elastic potential energy is 1/2 K value of the spring or spring-like elastic object times the square of the displacement, the end of the elastic object that's pulled or squeezed, how much that is displaced from its normal unpulled, unsqueezed location. So final displacement, that gives us the final elastic potential energy. And then initial elastic potential energy is 1/2 K initial displacement all squared. And then the last term is just 0, so don't need to write anything there. Okay, so we got 4 terms in here, and that's the number that we're trying to find. We know we have enough information, we know just about everything else, that we know the initial location is 60 meters and the final location is 0 meters. And then 40 meters just to stretch it, just to lay out the rope before it starts stretching. And then 20 meters of stretching. So the final elevation is 0. So that whole term there, the final gravitational potential energy is 0. And that's 60 meters. And then the initial amount of stretching in the rope is also 0. The rope didn't start stretching until well after the start of this process. So in the initial state, there's no stretching. In the final state, there's 20 meters of stretching. Initial amount of displacement for the end of the rope is 0. So that whole term, the initial elastic potential energy is 0. Now we're just left with 2 terms. 0 equals minus mass g initial. Let's say the mass of the jumper is, what do I like to say here, 70 kilograms. So mg y initial, 70 kilograms, 9.8 meters per second, and the initial elevation was 60 meters. And then this term, plus 1/2 k, we don't know that, that's what we're trying to find, times the final displacement after the rope has been fully stretched, squared, and the amount of stretching is 20 meters, not 60, not 40 either, 20. So that's enough. We can do all the numbers now and solve. "70 kilograms times 9.8 meters per second is the weight of the jumper, and that's going to be 686 newtons. And then newtons times meters gives us that potential energy, 60 meters. And this term has to cancel out this term, so they have to have the same magnitude. So this number here, the magnitude of the elastic potential energy, is equal to that, the final, or this is the initial gravitational potential energy, and it's equal to the final elastic energy. 1/2 k times 20 meters squared, or 400 square meters. And then just do the algebra. 1/2 times 400 just gives us 200 square meters, and divide both sides of the equation by 200 square meters. So K comes out to, let's see, where's my number? 206 newtons per meter. Newtons per meter is the normal unit label for K, because remember, where did that K first appear? It appeared in an equation for a force, the spring force. So the magnitude of the spring force is just K times the magnitude of the displacement. So strength of the spring force, or magnitude of the spring force, divided by the size of the displacement is K. A certain number of newtons divided by a certain number of meters, so K must have units of newtons per meter. And what that K actually means is this. Let's say K is, in this case, K is 206 newtons per meter. That's the amount of force needed to stretch the rope by 1 meter. 206 newtons of stretching force per meter of stretch. One last thing that I want to mention. Go back to thinking about gravitational potential energy. I've mentioned a few times that you can define your coordinate system any way you like. That is, you can put the zero level of elevation for potential energy purposes anywhere you like, because wherever you put that, that means you get different numbers for the potential energy at different particular locations, but you'd always come up with the same change in gravitational potential energy, and it is, after all, change in gravitational potential energy that matters. Right? Change in gravitational potential energy is what appears in the one essential equation. Just to demonstrate that, let's say coordinate system A. You've got some object and you raise it by some displacement from some lower level to some higher level. And let's say in coordinate system A, the initial location we'll call 0, and the final location we will call 10 meters. So in that case, what's the change in gravitational potential energy. Change in gravitational potential energy is just the final minus the initial, which is mg final elevation, which is 10, minus m times g times initial elevation, which was 0. So the change in gravitational potential energy when we were using coordinate system A is just mg 10 meters. Now try a different coordinate system. We'll still move the mass in the same way, but we'll give the locations, we'll give the elevations different names, different numbers. Still moving it up 10, and now we'll say that the initial location is minus 10 meters, and the final location is 0. The initial and final locations are still 10 meters apart, and up is still the positive direction. So in that case, change in gravitational potential energy, just final gravitational potential energy minus initial gravitational potential energy. So mg times final elevation, which is 0, minus mg times initial elevation, which is minus 10. And here we've got a minus 1 times a minus 1, which gives us a plus 1. So the change in gravitational potential energy when we were using coordinate system B is mg times minus 1 times minus 1, or plus 1 times 10 meters. Same thing. You get the same change in gravitational potential energy no matter where you choose to put the 0 level. So we always want to put the 0 level of elevation at some convenient place, like either the beginning or the end of the motion. One other thing worth thinking about here, and that is in a little bit more detail, say the simple case where our system is just one object, and since potential energies are shared by 2 or more objects, if you've got only one object in the system, that system doesn't really have any potential energies. It has nothing but kinetic energy. So in that case, the work done by external forces is just equal to the change in kinetic energy. That was an idea that you first saw back in section 10.3. And let's think about this case where a car is in a crash. It just skids off the road on a snowy, icy day and crashes into a barrier, and that brings the car to a stop. So here's the situation at the initial moment when the car first comes in contact with the barrier. So there's some initial velocity at the moment when the car first hits the barrier. That's the moment when the normal force pushing backwards on the car, the normal force from the barrier pushing backwards on the car, first starts to slow the car down. The car doesn't stop instantly. It takes a brief period of time to slow down. And so since it's slowing down over a brief period of time, it's still moving. And let's say this car has just a crumple zone, so that as the car keeps moving, the front end of the car just crumples up. And what we're left with in the final state, where the car has a final velocity of 0, it's been completely stopped. Now, Now everything, now this whole length of the car has been crumpled up and flat as a pancake. So the car traveled this distance while it was being brought to a stop. Or you could say this part of the car, which moved from here to here, right? This part of the car is right here at the initial moment, and then that same part of the car is right here, right up against the barrier in the final state. That part of the car had a displacement like that. So a displacement this way, while it was feeling a force, normal force from the barrier on the car, pointing in the opposite direction. So here's a force acting on something that's feeling a displacement. There's work done. Work done on the car. Actually, the net work done on the car will just be the work done by this force here. That any other, we're using the impulse approximation, where in some kind of a collision, the forces between the two colliding things are the only large, significant, important forces at all. So that the net force on one of the colliding objects is just that collision force that it's feeling. So the work done is just, remember our work equation, the magnitude of that force, normal force from the barrier on the car, times the magnitude of the displacement that the car went through while it was traveling that distance, just call that d, times cosine of the angle between force and displacement. So in this case, the displacement was this way. The car was moving to the right while it was being brought to a stop, while it was feeling a leftward force from the barrier. So the displacement direction and the force direction are perfectly opposite, 180 degrees apart. That angle is 180 degrees. Cosine of 180 degrees is -1. So the work done on the car is negative. Right? This is a magnitude, so it must be positive. This is a magnitude, so it's positive. And this is -1. So that means the work done is negative. So the change in kinetic energy is negative, obviously, because the change in kinetic energy was a loss of all the kinetic energy that the car started with. Let's just write this out in terms of our defining equations. The work done is this, which is just the normal force times the displacement while it was coming to a stop, times cosine of 180, which is -1. So -1, that's the cosine factor. Normal force from the barrier on the car times the distance traveled while the car was being brought to a stop, or I'll call that the stopping distance. And that's equal to the change in kinetic energy, which is just final minus initial kinetic energy, or 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. But of course, in the end, the car is brought to a stop, so the final velocity is 0. So that term is 0. So all we're left with is this, minus force times distance, stopping distance, equals minus 1/2 mass initial velocity squared, or minus the initial kinetic energy. There's a minus sign on both sides, so you can just get rid of it by multiplying the whole equation by 1, and we've got normal force, stopping distance, equals the initial kinetic energy, 1/2 mass initial kinetic energy squared. Now let's say, imagine we have a bunch of cars all hitting the same barrier. Cars of different sizes and they have different speeds at the moment they hit the barrier. But let's say that the barrier applies the same force to all those cars. Same normal force from the barrier on those cars. Same force felt by, same normal force on different cars. So this is the same number no matter which car we're talking about. So as we compare one car to another, this factor is a constant factor. And so only this factor changes when the kinetic energy changes. So we can say then that the d, the stopping distance, is directly proportional to the initial kinetic energy, the amount of kinetic energy lost, which makes sense. If you got more kinetic energy, you have to do more work to take away all of that kinetic energy. And if you've got the same force all the time, the only way to get more work is by having that force applied over a longer distance. So let's say our four cars look like this. Car A has a mass that we'll call just plain m, and an initial velocity at the moment it hits the barrier of that we'll call just plain v. Car B has a larger mass, let's say 2m, and its initial velocity is slower, only half the velocity of car A. And then car C has a mass of 3/4 the size of car A's mass, and its initial velocity is 4/3 car A's initial velocity. And finally, car D has a mass, let's say car D's mass is 3 times car A's mass. And car D's initial velocity is 0.6, 6/10 of car A's velocity. Now I can rank, the question is, rank those cars in terms of the stopping distance that they experience. But since this happens to be the case, then ranking in terms of stopping distance is just the same as ranking in terms of initial kinetic energy, ranking in terms of the amount of kinetic energy that collision got rid of. So when you do the numbers to make the comparisons, for example, it might go like this. We'll just call the energy lost by car A was its initial kinetic energy 1/2 mv squared. And the energy lost by B was just its initial kinetic energy, which is what? 1/2 a mass of 2m times a velocity of 1/2 v, and that velocity is squared. So what we've got now is 1/2 2m times v squared over 4. And that means this car's initial kinetic energy is just, we can write it as 1/4 times 1/2 mv, or rather we can write it as 1/2 times 1/2 mv squared. 1 half mv squared was just the initial kinetic energy, or the energy lost by car A. The work done on car A got rid of that much energy. The work done on car B got rid of only half as much energy. So only half as much work done on B. So the stopping distance for B was only half as large. When you, I'll leave it as an exercise for you to go through the other two and see where they come, where they fall into the ranking. But if you go through all the numbers correctly, here's the ranking that you should come up with. Car C had the biggest stopping distance, then followed by A, followed by B, followed by D. Right? We've just seen here that A's stopping distance was bigger than B's, and then if you do the rest of the algebra, you'll see where car C's, how much energy car C lost, in other words, how much work was done in car C, and the energy lost, or also known as the work done on car C, is just proportional to the stopping distance of car C, and that would have the longest stopping distance. So give that a try just to finish that, and convince yourself that that really is the ranking. Nothing new after this. It's all practice on stuff that we've seen before. I'll have more to say on what kind of things to practice for the final exam in a final video, which will be out in the middle of the week. Look at your schedules in Blackboard information to see when that comes out. But now try the lecture exercise if you haven't already tried it, and the homework assignment, which will be coming out very shortly.